Imagine a vast ocean of jittering possibility, dense and alive. Before the Big Bang, space might have behaved like a boiling quantum sea. That means time and space, as we know them, could be emergent phenomena. Picture small bubbles forming, colliding, and producing a vast expanding region. Emergent means the familiar universe appears from deeper rules, not from an absolute nothing. This matters because it changes our story about origins and about what we can test. Tiny quantum fluctuations can create structure, and they can seed whole universes. Mechanisms that let geometry fluctuate and then settle play the starring role. Paths include quantum bounces that reverse contraction into expansion and tunneling events that nucleate new regions. For example, one-loop quantum model predicts a bounce when density reaches about Planck density, roughly 10 to the 94 grams per cubic centimeter. That number shows why ordinary physics breaks down at extreme density. So the immediate picture is that before might mean a different kind of physics, not empty silence. Picture a dim hall of warped mirrors reflecting strange light. When cosmologists say before the Big Bang, they mean a regime where classical spacetime no longer applies. This matters because our usual clock and ruler lose meaning in that regime. The mechanism involves equations that blow up and quantum effects that take over. General relativity treats spacetime as flexible fabric, and it predicts singularities where curvature becomes infinite. Quantum physics makes that fabric fuzzier, with geometry subject to uncertainty and fluctuations. For example, in classical models extrapolating backwards, the scale factor shrinks to zero within finite time. That scale factor value equals zero at a classical singularity, and energy densities diverge. The takeaway is simple and important. Before is a label for where known equations fail, not a clear historical epoch. Imagine squeezing a rubber sheet until threads start to fray at the center. Singularities are points where the mathematical fabric frays beyond repair. This matters because predictions stop being meaningful at that break. Quantum gravity candidates act by replacing infinite curvature with finite, governed dynamics. They make geometry grainy, and they add repulsive quantum pressures that halt collapse. In loop-inspired pictures, discrete loops of geometry create a bounce when density reaches near Planck scale. A concrete number helps. Planck length is about 10 to the minus 35 meters, and loops operate at that tiny scale. Observers within coarse-grained spacetime would see an expanding universe emerge after the bounce. So classical infinities give way to regulated, finite behavior under quantum rules. Picture a contracting universe collapsing like a deflating balloon, then snapping back into expansion. A cosmic bounce is the idea that contraction reverses and creates expansion. This matters because a bounce gives a causal predecessor to our universe. Mechanically, quantum discreteness or high-energy corrections introduce effective pressure terms that counteract gravity. These terms act when curvature or density approaches Planckian values. One concrete example comes from loop quantum cosmology, where precise effective equations show a bounce at densities near 10 to the 94 grams per cubic centimeter. Numerical simulations of simple models produce symmetric bounces, and they preserve large-scale information across the transition. The anchor is simple. Quantum corrections can convert a singular crunch into a smooth bounce that births expansion. Envision a tapestry of vibrating strings stretching across hidden dimensions. String cosmology suggests the early universe could arise from string and brane interactions. This matters because extra dimensions change what counts as a singular beginning. Mechanisms include colliding branes, winding modes that stabilize dimensions, and symmetry-breaking transitions that release energy. In one evocative scenario, two branes collide and transfer enormous energy, creating a hot expanding region that looks like a Big Bang. A numeric estimate helps. String tension is often tied to energies near the grand unification scale, around 10 to the 16 gigaelectronvolts. Models show that compact dimensions can unwrap and that effective four-dimensional physics appears after such events. So strings and branes offer a concrete, higher-dimensional route to a prehistory. Imagine a rhythm of contraction, then gentle reheating, then expansion repeating over cosmic time. Cyclic models propose the universe undergoes many such cycles. This matters because cycles remove the need for a unique creation event. Mechanisms often use slow ekpyrotic contraction to smooth and flatten space, followed by a high-energy transition that triggers expansion. In some models, entropy generated in each cycle is diluted by expansion spanning many e-folds, so observable conditions reset. A practical number, ekpyrotic phases can last many orders of magnitude longer than radiation eras for stability reasons. Simulations indicate cycles can produce nearly scale-invariant perturbations similar to inflation under certain conditions. The takeaway is clear. Repeated cosmic epochs can stand in for a single mysterious origin. Picture an immense landscape with countless bubble universes popping like soap bubbles. Eternal inflation and related ideas suggest our universe is one pocket in a much larger multiverse. This matters because it changes what counts as an explanation, and it shifts probability into the foreground. Mechanisms include quantum fluctuations of the inflated field that create nucleation events and landscape dynamics in string theory that permit many metastable vacua. For example, inflationary calculations predict roughly one new Hubble volume forms per e-fold in some setups, leading to exponential production of pockets. Estimates can produce astronomically large counts, easily exceeding 10 to the hundreds in some landscapes. Observers then ask conditional questions about typicality and selection effects. So the multiverse reframes cosmology as a statistical enterprise across many realizations. See a calm observatory, detectors humming softly under starry skies. Testing pre-Big Bang proposals matters because empirical evidence separates plausible models from metaphors. Mechanisms for detection include primordial gravitational waves, specific spectral tilts in the cosmic microwave background, and relic particle abundances. Gravitational wave amplitudes from a bounce or pre-inflationary phase could peak at frequencies accessible to future detectors between millihertz and kilohertz. For example, a predicted stochastic background with energy density around 10 to the minus 10 of critical density might be visible to proposed space interferometers. Another concrete probe is searching for small deviations in the CMB at multipoles near L equals 20 to 40. Experimental programs like Next Generation, CMB satellites and space-based interferometers can push these limits. Bottom line, observational windows exist, and they keep speculative models anchored to measurable reality. Remember the immediate image from the hook, the quantum sea birthing our space. We saw several concrete ways physics allows a before: regulated bounces, string collisions, cyclic epochs, and multiverse nucleation. Each idea changes what before means, and each offers mechanisms that create observable signatures. Measurements such as primordial gravitational waves and specific CMB anomalies act as litmus tests for some proposals. A reasonable next step is to follow experimental progress in gravitational wave astronomy and precision CMB missions. If detectors find predicted signals, the speculative scaffolding becomes testable science. So the calm conclusion is this: current physics gives coherent, diverse stories of a prehistory, and experiments can actually adjudicate between them. If you found this surprising, there is much more to explore.